Hello, my name is George Driessche. I'm a scientist at Biogen, and today I will be co-presenting with Steve Emrick from USP, and we will be providing an overview about how the modeling working group operates to develop allotrope data models, also known as ADMs, that help build a path towards interoperable lab data. So Steve will kick us off by answering the question, why do we need data models and how do they support interoperability? Then I will take over and begin to answer the question of what is an allotrope data model and how do ADMs help drive the ASM generation, and then provide an overview of the modeling working group business process so that anyone who wants to join the working group knows how they can sponsor lab instruments to generate an ADM that they can then begin leveraging. Steve, I'll let you take over.
Thanks, George. It's good to be here today. So, like I said, like George said, we're going to talk about the need for interoperability and how the work of the data modeling group supports that. Next slide, George, please. Are you able to advance? Great, thank you. So I think that this goes back to kind of how Vinny level set at the very beginning on the overall cost of drug development, and how much does kind of data wrangling go into that. I like this slide because it shows just how much volume of data are being generated in healthcare and across life sciences today. 2,300 exabytes in 2020 of healthcare data generated. I don't have the exact numbers on pharmaceutical R&D and QA/QC, but I imagine that it's approaching that, or maybe even exceeding that level. Everybody wants more data. We all want to make decisions that are based on data, but that's actually very hard to do if your data are messy or of low quality, or just talking about the same things in different ways. And I think that we've all been there for the people that are familiar with data. If you're a data scientist or an informaticist, it can take a lot of time. You spend your time on cleaning things up and on lower value activities, as opposed to leveraging good, clean, structured, standardized data as a means to drive decision support, which is really where we all want to get to in this space. Next slide, George, please. Thanks. So here's an example of where we're starting from in many situations today with analytical chemistry, and certainly where I sit at USP. If you look at our monographs or general chapters, they're often written as prose. There's lots of free text, unstructured data, but if you kind of peek under the hood, there are conceptual domains that are identifiable. So if an analytical chemist was looking at this text, he or she has been trained through their education to recognize certain things. So they understand that there's a UV detector involved in this method. They understand that it's from water. They understand that there's a C18 column, the specs of that column, but that's all done through their education and training. Can you advance that, please, George? So how do we train a machine to scan over that same text and pull out the essential pieces of information that would be needed to support reproducibility, full context, look back, decision support of the data that are captured by a free text analytical method? Well, we can't do that unless we've got some type of underlying foundational ontologies or taxonomies. And that's a lot of what the work of natural language processing is. And I wanted to start with this example because I think it builds up nicely to the work of what the data modeling working group does. Next slide, please, George. So when we map those things to the various ontologies like Allotrope, we can achieve better classified and better structured data. And why do we want to do that? Well, Classifying and structuring data allows us to decide what things are important enough to name, to classify, to relate to each other, the entities, the attributes, the relations that go into a data model. And the more that we can do that, the more that we can agree, regardless of vendor implementation, how those things are called, the higher quality and the more interoperable our data are, and the easier it is to look back at what happened during an experiment, regardless of the platform or the software type or the vendor that you were using. So this enables consistent search and retrieval of information across data sets, lets us make decisions at scale, spot outliers. It provides a common nomenclature and framework for interoperable data exchange, and it allows software and other tooling to enforce the model constraints upon data entry and creation. And that's important because I think that as these tools advance and as the data standards advance, we're going to be getting away, and we already are starting to get away already from writing these things as prose to a place where we're creating the data as structured data from the beginning, right? So that supports the entire idea of better data capture from data entry, right? Which supports the larger quality framework that we're trying to get to. Next slide, George. And so when we analyze text like that, then we can start to be able to index and classify things according to an ontology like Allotrope to define things like equipment, materials, roles, processes, and tag those things accordingly so that a machine can recognize them as it's scanning over those texts. Next slide, George. And what we might end up with is something that's similar to what some of you are familiar with Allotrope graph models that relate things like these in a very structured way. And I wanted to show this slide because I think that some of the things that George is going to talk about are showing a next generation of an approach to modeling where you don't always have to rely on a graph model, but you can model things from the beginning in a tabular way and then generate these allotrope simple models out of it that can be connected back to the foundational ontology for full context and retrieval of those information. But it provides a more rapid framework for that model development. And so with that, George, next slide.
Thank you, Steve. Steve laid out a very strong use case for a data model, the data ontologies. But then the follow-up question to that is, where does a data model fit into your organization? Vinny earlier showed how standardized data can lead to use cases in a fair compliant system where users can engage with those standards through their ELNs, their business informatic platforms, or data science toolkits. But where things start is over here on the left-hand side of the screen with our lab instrument systems. So our complex or simple integration instruments, that can be something like a CDS, a mass spec, qPCR plate readers, and our lab metadata systems with electronic lab notebooks, LIMS, or other systems. And one of the first components that are needed in order to utilize the data here is an Internet of Things connecting technology that creates a data pipeline that goes from these siloed environments into a singular raw storage environment. And once the raw data is stored, you need a toolkit like a data converter that is either developed in-house, it can be developed by a third-party vendor, or from instrument vendors themselves that fits the data model to that raw data to create your standardized format. And where the modeling working group plays a role is in this center component here with our data models. We are working on the process of developing ADMs to fit for our lab instrument data so that it's structured and standardized. The modeling working group is not working on the development of data converters. That is something that's outsourced to either in-house teams for individual companies, third-party vendors, or in some instances, the lab vendor themselves are outputting the data converter toolkits. So what is an allotrope data model? An ADM represents one or more use cases across the lab. And these use cases use RDF graphs to describe them. So it's taking a collection of terms, instruments, and processes that support an analytical process and fitting it all into a centralized model. You can then use that model to connect it with your data so that the entire lab process is described within a standardized file, such as an ADF with read and write capabilities. And it's important to know that all of the data inside the ADF is described and interpreted with that ADM, with that data model. The reason why an ADM uses a tabular approach or aggregation, those two terms are actually being used interchangeably now. And a big advantage of this is that it's a simple structure that leads to reusable queries, but importantly for the scientists, it's an Excel-based creation. So shown below is an example of an ADM draft. There are several fields in here, such as your parameter type, that describes whether it's a metadata term or a result. But then the key values come from things like parameters. Those are the actual instrument outputs that a scientist would interact with on a daily basis. So the scientist can take the raw output from their instrument, like measurement ID or run date, insert it into a Excel column like so, provide a label and a description and an example parameter value, and then send that Excel document to the modeling working group, where the modeling group then begins semantically defining those terms. And that's the first step to creating this data model that standardizes your information. This leads to easy association of key and value pairs. It is a first step towards a graph description. Some of the drawbacks to this approach, though, is that until it's fully connected back to an AFO, there's limited context that's described. Due to limited semantics and context, this is a less machine understandable format than a full graph description. And it's not easy to interrogate the data with a simple query. It requires multiple queries to begin understanding the leaf node values and hierarchy. So the data flow using a simple model versus an ADM is both processes start at the top left, where you take your instrument terms, they get mapped to the proprietary terms are mapped to an existing AFO, and a ADM model is developed. So modeling according to ADM. And at this step, there's a branching that occurs in the two pathways. Some groups can continue forward and can begin containerizing their data with an ADF. And so they're following a semantically rich data flow that leads to an application that some groups will be talking later about on days 2 and 3. However, as Vinny mentioned, there's this new ASM allotrope simple model, JSON representation that's being developed. And so during the governance process of ADM, there's a compatibility conversion test that's performed that allows that model to be represented as an ASM JSON. So now this creates what is called a simple data flow with a lower barrier to entry for some groups to begin accessing that ASM data structure and developing their use cases. But the important thing here to know about both these pathways is that all the terms are mapped into an ADM model first. The ASM is created from the ADM, and there are two pathways for leveraging allotrope data. The overall business process of the working group is as follows. A company rep sponsors an instrument for model development. That company rep works with their SMEs to begin drafting a priority term list and formally defines a model use case. So for an example would be the qPCR model is used for DNA quantification. Once they have that model use case in the draft list, the company rep and SMEs attend a modeling working group meeting, share the model, their draft model with that team, and then those terms are reviewed. Semantic engineers in the group ask the SMEs questions about what does this definition mean, how is this working, and then the the semantic engineers begin semantically defining those terms and adding them into the AFO. After the semantic engineers complete that process, they share the model back with the working group and SMEs to provide their feedback. Are these semantically defined terms accurate? You repeat this process 2 to 3 times. And then finally, that model is submitted to the Allotrope Foundation governance process. So an overview of the various roles within the working group. The scientific SMEs are responsible for sponsoring models and capturing that first generation of terms. The semantic engineer SMEs are identifying existing terms in the AFO, begin the process of defining new terms for the AFO, and then sending those new terms back to the modeling, to the SMEs who review term definitions. And the scientific SMEs are also providing sample instrument files so that when we answer the question, is this model agnostic, we can say we have two or more instrument vendors to compare against for a particular assay type. That tabular model is then finalized by the semantic engineers, and it is submitted to the governance process where it will eventually be released for public review. During the governance process, there are 5 phases. And phase 1 is the ideation and development of a model. Phase 2 formalizes the draft of the model and addition of terms. Phase 3 is the formal review of that model. Phase 4 is a public review. And then phase 5 is the release of the ADM and AFO. Shown here is the workflow for the 5-phase process, where the SMEs are starting with the development of the terms, formulating the draft model, identifying new terms, and preparing for submission. Phase 3 begins the formal review of that model, where SMEs and semantic engineers are receiving submission, providing an estimate of work, generating the URIs, aligning new taxonomy terms, and then eventually progressing forward to the public release and public review of that model. It's important to note that the public release, the goal is to have those on a quarterly basis. And I will hand it back over to Steve here for the conclusion of our talk.
Thank you, George. I really like the approach of the tabular models and the focus on the leaf nodes. I mean, it does remind me of other terminologies that are used in the world. If you look on the clinical side, CPT codes or ICD, they do have a hierarchy, but the things that are submitted for a certain purpose are it's the diagnosis code. It's not the entire ontology. So I really think this is very useful to support a more agile and rapid development of the modeling. And to kind of hit that point home a little bit more, I took a look at the product releases page on the Allotrope website, and it turns out that around 80% of the models in Allotrope are tabular models that can be converted to ASM that don't require the full graph implementation. So I think that underscores some of the points that George was mentioning, and these use cases like qPCR for DNA quantification or FTIR to help substance identification. These are common use cases across the industry, and having a more agile and rapid modeling development capability, I think, benefits the overall community in terms of getting to higher levels of interoperability and data standards. Next slide, George. And so with that, we'll wrap it up. Just a few points here, housekeeping notes. If anyone is interested in joining the modeling working group meetings, they're every Wednesday at 11 o'clock. You can contact Benjamin Wolford Lim to be added to the listserv. There is the product releases page that we just showed a little bit of earlier that you can find on the Allotrope website, as well as the overall ADM governance process. And the official repository for all of the ADM Allotrope artifacts is at GitLab. And so with that, George and I are happy to take questions.